All right, so let's get started. Last class, we ended by reviewing how to draw Lewis structures, and we did some practice. We're going to get a lot more practice today. And most of the elements that we deal with when we're drawing Lewis structures, most elements want to have 4 pairs of electrons around them, but we saw some exceptions. How many pairs does hydrogen want next to it? 1 pair. How about beryllium? 2. Boron? Okay. 3. Most elements, however, guys, want 4. There are elements that can exceed the octet rule, meaning they can accommodate more than 4 pairs. Now, it's not just any element that can do that. The elements that can do that, if you're looking at your periodic table, first of all, we're talking nonmetals here, okay? When we draw Lewis structures, they're for covalent compounds. So, nonmetals on the 3rd row. So if I'm looking at my nonmetal area, 3rd row elements like phosphorus, sulfur, chlorine, or any element below that, the reason those are the first elements that can do that is because those are the first elements that have d orbitals available. Okay, now think about it. If you think, where the d sublevel is on your periodic table, what's the first row of d? Is it 1d, 2d, 3d, 4d, what? 3d. Okay, so elements on the 3rd energy level, like phosphorus, sulfur, chlorine, those are the first nonmetals that have d available. Okay? And we're going to do some practice with this. And we're going to start off by drawing their Lewis structures. Do you need to, do something differently than we did last class in drawing these structures? No, you don't. Okay? I'm going to do one with you as an example. Chlorine trifluoride. Okay? And our first step, guys, remember, is always figure out what's the central atom. What do you think it's going to be? Chlorine, okay. Let me change colors here, okay. Let's tally up our total electrons. Chlorine has how many valence electrons?
7.
Okay, 7. There are 3 fluorines. Each fluorine has 7. Okay, so that's 28. How many pairs is that?
14.
Okay. We're going to draw a framework. Chlorine in the center. Just in drawing this framework, I've used up 3. So I don't have 14 pairs available. I now have 11 pairs. And anything that you have left over, what are these called? What kind of pairs are these? Lone pairs? How do you draw them? Dots? Where do you put them first?
The
Terminal elements. Okay, great. 1 pair, 2 pair, 3 pair, 4, 5, 6, 7, 8, 9. Where do you put any that you have left over? On the central. No matter how many you have left over. I did 9 lone pairs. I have 2 more. Both of those extra pairs are going to go on the central atom. how many pairs does this chlorine have around it now? 5. That is exceeding the octet rule, and that's okay. Chlorine can do that. It has available d orbitals. Okay, so I didn't have to do anything differently in my steps for drawing this Lewis structure. Okay? You guys try the other 3 on your own. All right, check them. Now, ladies and gentlemen, let me say one more time. I said this last class, but let me say one more time that the shape in which you draw your Lewis structures doesn't matter. I saw multiple people draw this one in like an L shape. That's totally fine. Doesn't have to be drawn straight. As long as there are the right number of lines and dots in the appropriate place, you're good to go. Okay? Now, this last one here, there might have not really seemed anything all that odd. Do you know why I put this compound on this exceptions slide? Yeah, it's got a noble gas in it. That's kind of weird. Okay? Noble gases typically don't bond with other things, but they can. All right? Some of the larger noble gases like krypton, xenon, radon, you will sometimes see them in compounds, whereas the lighter ones, helium, neon, argon, basically never. All right? But the take-home message here is, did you have to do anything differently? No. I saw a few people trying to put in like a double or a triple bond here. Guys, remember, a double and a triple bond, that's only necessary if something doesn't have enough pairs. These have more than enough. We definitely don't need any double or triple bonds. Okay? You fill up your terminal atoms, and any lone pairs left over are put on the central atom. Okay? Okay, so we're going to talk about our next topic, which is something that some of you may have covered in honors. It's a topic called resonance. And the example that I have on this slide, I'm not crazy about, so I'm going to draw another example, a different example. Okay. I have just drawn the Lewis structure for nitrite, the polyatomic ion nitrite. Which one is the correct one? Ha! Trick question. They're both correct. Okay? But how are they different? I mean, what's the one thing that is different about those two drawings? Yeah, the location of the double bond. Does it matter where you draw it? No. Those are both drawn correctly. Well, guys, there's an issue here. There's a concept called resonance. If you can draw more than one Lewis structure for the same compound, simply by, putting the double or a triple bond in a different place, that is an issue of resonance. Okay? Now, let's just back up for a second. Guys, when I draw like just a single line like that, what does that line actually represent? A shared pair of electrons. A double bond is 2 shared pairs. That second pair of electrons doesn't actually sit in one position. It doesn't sit on this side either. Okay? It can move back and forth. right? And so what you end up getting, if you were to actually see, like look at a molecule of nitrite, you would not see this. You would not see a molecule that has a double bond on one side and a single on the other. Here's what you would see. And I'm going to draw something right here that I don't ever want to see you draw on a test. What I'm going to draw here, you will not be allowed to draw on a test. The College Board would not accept it, nor would I. Here's what nitrite really looks like, and I'm going to do my best here. It's kind of hard to draw with this particular technology. I know that's really hard for those of you that are in the back to see. It's not a single bond, but it's not a double bond either. It's like a bond and a half, okay? It's a bond and a semi-bond, okay? If you were to describe this bond, it's not a single bond, it's not a double bond, it's like a bond and a half. There is a term that we used last class, and I said, write it down, we'll come back to it later. This is when we're going to use it. This was the term. Bond order. Okay? Nitrite has a bond order, not of one, they're not single bonds, not of two, they're not double bonds. It has a bond order of 1.5. Okay? But guys, this is what nitrite really looks like. Okay? I have seen questions addressing this very issue, saying things like, explain why nitrite's two bonds are identical. Okay, and at first, if you were to only think of this, you might say, well, that's not true. These two bonds are not identical. That's a single, that's a double. This is not how nitrite really exists. This is how it exists. Okay? Now, here's the thing, guys. You're not allowed to draw this. Unfortunately, if you're answering a resonance question in free response, what that means is you have to draw both of these. And I know that's a pain. Okay. Let's do like an example question in dealing with resonance. I'm going to draw another molecule that also experiences resonance. That's nitrate. Nitrate also experiences resonance. Now, how many total structures would you have to draw to show all of the different ways that that double bond can be arranged? 3. Okay? You'd have to draw 3 resonance structures. Okay, now see if you can figure this out. If nitrite has an average bond order of 1.5, what would this guy have? What's that? Not 5 over 3. You're close. 4 over 3. Okay, because this is where this number came from. 1, 2, 3 bonds split between 2 locations. 3 divided by 2. 1, 2, 3, 4 bonds split between 3 locations. 4 divided by 3 is 1.3 repeating, 1 1/3. Okay. Now I'm going to give you a sample question in just a second, but remember that we are still in this time where You have to be able to explain things. Vocabulary is very important. This pair of electrons that moves locations, okay, you can call that a resonating pair of electrons. That's one way you could call it. A resonating pair of electrons. Or, if you want to be fancy, because I know that you do, you could call this pair of electrons that can move around, you could call them this. Delocalized electrons. And guys, just in everyday language, the word localized means something that doesn't move around a lot. Delocalized can move around. Okay. Here's what a sample question might be, and this is a good one. Nitrite versus nitrate. Which one of these has the shorter average bond length? Nitrite versus nitrate. Which one of these has the shorter average bond length? Okay. Don't answer immediately. Okay, this has a bond order of 1.5. This is 1.33. What's the bond order of just a single bond? What's the number? 1. What's the bond order of a double bond? 2. Think back to that rubber band demo. Is a single bond relatively long or short? Long. Okay. Which one of these? I asked you which one is the shorter. Which one of these has a bond order closer to a double bond, which is shorter? This guy. Okay. So both of these compounds have resonating electrons. Okay, let's say this is a free response question. Please don't shoot the messenger. Do you know how many, to answer this question, do you know how many resonance structures you'd have to draw total to answer this question? 5. I know that's such a pain. You'd have to draw out all 5 structures. These 2 and 3 for this one. Okay? And you'd say something about the fact that, although they both contain either resonating electrons or delocalized electrons, nitrite has a bond order of 1.5. Nitrate has a bond order of 1.33. This results in a shorter bond length, something like that. Which one of these, just to make sure you've got this, which one of these has the weaker average bond strength? Weaker. Nitrite or nitrate? Nitrate. Weaker bond strength. Remember, single bonds are weaker than double. This guy's closer to the characteristics of a single bond than the double. Now, a couple of things here. Just because nitrite experiences resonance, does that mean that when you're answering a question for something like nitrite, no matter what the question is asking, do we always have to draw out both of those structures? You only have to draw them out if it's a question that has something to do with resonance. If you were answering a question that just says, draw nitrite and tell us what shape it is, you don't need to draw both of them. That has nothing to do with resonance. The other thing I want to make sure you guys are clear on is, does every compound with a double bond have resonance? No, some do, some don't. Okay, like, I'm just going to make up some molecules. These probably don't even exist. Tell me this. Forgive me for not drawing in all my lone pairs. Does that molecule have resonance? Yes or no? Yes. How many resonance structures does it have? Two. I could have the double bond there or there. If I move the double bond over here, then I'm changing too many things there. That's not a resonance structure. So this would have two resonance structures. Let me give you one more. How about that? Does that have resonance? No, it doesn't. Okay. So not everything with a double or triple bond has resonance, but some things do and some don't. Okay. Let's move on to our final topic in this chapter. Which is a concept called formal charge. Okay, formal charge, ladies and gentlemen, is a topic that comes up, particularly when we're talking about elements that can exceed the octet rule. And the point is that when you're dealing with things that can exceed the octet rule, there are many, many ways, many possible ways to draw a Lewis structure for it. Some that can look extremely bizarre. And most of the time, what a formal charge question will look like is you might be given 2 or 3 different Lewis structures for the same compound. And those structures would already be drawn out for you. And the question would say, using the concept of formal charge, determine which structure is the best. Which one is the most appropriate? So I'm going to use as an example. I'm going to use the polyatomic ion sulfate as our example. And guys, if you were using our rules from last class of just drawing a Lewis structure, this is what sulfate would look like. But I'm showing you an alternate way that you could draw it, like this. Now, just to be clear, how many pairs are around this sulfur? 6. That's exceeding the octet rule. And that's okay. Sulfur's in the 3rd row of elements. I can do that. Sulfur can do that. Would I ever expect you to be able to just come up with this semi-bizarre structure? No, probably not. But I'm showing you these two, and I'm going to say, let's use formal charge to decide which one is the more appropriate structure. So what do? We are going to calculate a formal charge for each atom. And that sounds like it's something that's going to take a long time. It's actually not. Okay? And this is how you do it. Okay? Let's start with this oxygen, for example. Tell me, please, how many valence electrons does oxygen have? How many? 6. Okay. When we look at Lewis structures, guys, how are lone electrons represented? Dots or lines? Dots. Okay, so I'm going to just write that word above it here. How about bonded or shared pairs? Those are lines. Okay. This oxygen, how many dots, lone electrons, are around it? Okay, 6. How many lines are next to it? 1. What's 6 minus 7? -1. Okay, good. So this oxygen has a formal charge of -1. We're going to do that for every element, which isn't going to take us very long because, yeah, isn't this oxygen exactly the same as this one? It's going to give us a formal charge of -1. So is this one. So is this one. So is this one. Okay. Let's come back to this sulfur. How many valence electrons does sulfur have? 6. How many lone electrons are around that sulfur? 0. Plus how many lines? 6 minus 4. Okay. Now this oxygen is different. What's going to be the formal charge of this oxygen? Zero. Same with this one. How about this? 0. Okay, here's how we're going to make this decision. First of all, if you're doing a problem like this on a test, you don't have to show this kind of work or anything. I would, however, write in the formal charges into the drawings. As I said, guys, these Lewis structures would already be given to you. Here's how we make the decision. The better structure is the one that has more formal charges equal to 0. The better structure is the one that has more formal charges equal to 0. So, which one is the better one? Second one, yeah, the one on the right. Okay, this is the better structure. And when I say better, like having a formal charge equal to 0 essentially means an element at its low energy state. And elements always want to be as low in energy as possible, just like we do. Okay, that's why we like to take breaks. Okay? But that's all you'd have to say to explain yourself. The structure on the right is the better structure because it contains more formal charges equal to 0. So that's the end of chapter 8. I will tell you that the big overarching topic in chapter 9 is shapes. Okay? Looking at a Lewis structure and being able to tell me what its molecular geometry is. What is its shape? And in Chem 1, you learn 5 or 6 of what I consider to be kind of the basic shapes. We are going to go beyond that and learn some of the extended shapes for things that can exceed the octet rule. Okay? So at this point, we know how to draw things. We're going to talk about shapes. That's what VSEPR means. Anytime you see that, VSEPR, which really should be pronounced VSEPR, but we say VSEPR, that just means shape. And then at the end of the chapter, we won't do this today, we'll talk about something called hybridization. Okay? Now, this is an acronym. Do you guys know what these letters stand for? Let's try and figure it out. What do you think V stands for? Very. No. Valence? Super. No. Shell. Valence shell. Electron. Pair. Radiance. Repulsion. Valence shell electron pair repulsion. Here's the thing. First of all, guys, you've got to get your brains out of 2 dimensions on paper and into 3 dimensions. Now, that is easy, very easy for some people and exceptionally difficult for others. It depends on what kind of a learner you are. If you're a visual spatial kind of person, you love this. If you're probably more of like an auditory learner or a kinesthetic learner, this may be really difficult for you. But the point is, molecules take the shape that they do because electron pairs, doesn't matter if they're shared pairs, lone pairs, doesn't matter, they will spread out in 3 dimensions to get as far apart from each other as possible because electron pairs repel each other. Why? Same charge, yeah. Like charges repel each other. So these shared pairs, these lone pairs, they will spread out in 3 dimensions to get as far apart from each other as possible. So we're going to look at a whole bunch of shapes. Okay, come back to this. And here is what I would do. If this were me taking notes, I would create a little chart in my notes. And actually, we're going to make more columns than this. Steric number, bonding pairs, lone pairs, shape. Let's add another column beyond that for bond angle. And even another column for polarity. Because we're going to talk about all these things for each shape. And I'll explain what this term means, because this is probably new to most of you. So for each shape, I'm going to give you an example. We'll look at its Lewis structure. And I'm going to move pretty fast, so here we go. And here is our first one. Most of the examples we're going to do today, you have already drawn, maybe today, maybe last class. So if you go back and look at your notes, you will find these Lewis structures. So here's carbon dioxide. Okay, now, when you are trying to figure out what shape a molecule has, first and foremost, your eyes should be focused on the central atom only. Okay? And I want you to imagine that there's like a box around that central atom. This term, steric number, what I'm essentially asking you is, how many sides of this box have something coming off of it? And what's the answer for this one? 2. Carbon dioxide has a steric number of 2. Bonding pairs, that means of those 2 sides, how many of those sides have a bonding pair, or another way to say that would be a shared pair? How many of those 2 sides have a shared pair on it? 2, both of them. Okay. Are there any lone pairs on the central atom? That's all I care about. No. So guys, these two columns will always add to equal that one. And ladies and gentlemen, our first shape is linear. And it's at this point, I'm actually going to switch over to a program that one of my very, very closest friends showed me, who also teaches chemistry. Let me switch over to, here it is. Yeah. I'm going to put the link to this website where you can create any shape you want. Okay, and you can rotate it around. Okay. But that's what carbon dioxide looks like. It's linear. You probably could have figured this out without being told. The bond angle, 180 degrees. Okay. And let's think back to last class. Is linear a shape that is usually nonpolar? What do you guys think? Polar, nonpolar? Nonpolar. Do you remember the wording? Well, I mean, this molecule contains polar bonds in it. Linear shape, what's that phrase? Cancels out the polarity of the bonds. Now, just to make sure you've got this, what if I did this? Have I changed the shape? No. This would still be linear, but it wouldn't be nonpolar anymore. Guys, when we say things like linear is a shape that cancels out the polarity of the bonds, we're assuming that the terminal atoms are the same element. If they're ever not the same element, automatically polar, no matter what. All right, here's our next example, which we did last class. How come it's okay that boron only has 3 pairs next to it? I thought everything wanted 4. Good, it's an exception. Okay. What would be the steric number around that boron, central atom? 3? How many bonded pairs do you see? 3. No lone pairs. Okay. That, ladies and gentlemen, is trigonal planar. Do you know what the word planar means? Flat. Yeah. Okay. If I rotate this like that, you can see that it is flat. Okay. It's got 120 degree bond angles. And what do you guys think? Polar, nonpolar? Nonpolar, assuming that what? Yeah, all of our terminal elements are the same. Okay. Yep, trigonal planar is a shape that cancels out polarity of the bonds. All right. Moving along. Here's our next example. So for sulfur dioxide, what's the steric number? 3. 3. Remember, steric number means how many sides of the box have something on it? 3. Of those 3 sides, how many have a shared pair? 2. One side has a lone pair. here's what that looks like. Okay. This thing up here, that's representing that lone pair. Okay. So guys, here's how I want you to think about this, okay? And if you go and use this at home at all, this simulation here, it says electron geometry, trigonal planar. That means it has a steric number of 3. So it's like you started out with something trigonal planar, but then you pulled one side off and replaced it with a lone pair. This is bent. Okay. Now here's the only thing I don't really like about this simulation here. The bond angle is not quite 120 degrees. It came from something trigonal planar. The electron geometry is trigonal planar, but here's the thing. Lone pairs take up more space than shared pairs. Okay? Lone pairs take up more space than shared pairs. These two guys, it's like they're pushed a little bit closer together. So all you have to say, you don't have to give an exact number. For bond angle here, all you have to say is less than 120. Thank you. Okay, you don't have to give an exact number, less than 120, because lone pairs are pushing those two shared pairs a little bit closer together. And what do you guys think? Polar, non-polar? Polar. Bent is a shape that does not cancel polarity of bonds. Okay, here's a quick one. What's our steric number? 4? How many bonded pairs? 4. Any lone pairs on the central atom? Nope. So this tetrahedral, ladies and gentlemen. Okay? And it has a very exact angle, 109.5. Write it down. You are responsible for knowing it. Okay, 109.5. Polar, non-polar? What do you think? Non-polar. Tetrahedral is a shape that will cancel out polarity. Moving on. Steric number, please. 4. Bonded pairs? Lone? Okay. So electron geometry is going to be tetrahedral. It has a steric number of 4, but imagine tetrahedral and then pulling one of those shared pairs off and replacing it with a lone pair. You get trigonal pyramidal. And that's what it looks like. It's like a short little tripod. And again, this isn't quite correct. Okay? Lone pairs take up more space, so what do you think you should write for bond angle here? Less than 109.5. You don't have to give an exact number. Polar, non-polar? Polar. Okay? Here's our final one that is basic, the basic shapes. And this one you should be able to draw in your sleep. Steric number. 4, 2, 2. Ladies and gentlemen, that is also called bent. What makes this bent different from the other one?
There's two pairs.
Yeah, there's 2 lone pairs on this one. The other bent only had 1. Okay. Bond angle, this morning somebody said, oh, the bond angle must be like less than 109.5. You don't have to write the symbol twice. You can just say less than 109.5. Okay, but guys, this is probably, believe it or not, this is probably the most missed shape. Because notice how I have drawn my Lewis structure. A lot of people, for whatever reason, this particular one, a lot of people would draw it like this and say it's linear. I've drawn it linear, but that's not what its shape is. This is probably the most missed situation right here. And guys, is water polar or non-polar? Polar, definitely polar. Okay. That's where you stopped in Chem 1. We are going to go beyond that now because we are big league. We drew this one right at the beginning of class today. Okay. What's the steric number now? 5. 5 bonded pairs, 0 lone pairs. Trigonal bipyramidal is how you name that. Okay. Trigonal bipyramidal. Now, we've got the model up here. I've also got a model kit up here that I'm just going to keep in this room in case people want to use it. So I've built this right here as well, okay? And I want you to notice some things about this model, okay? With trigonal bipyramidal, you have a completely vertical portion of it. But you also, if you, let me try and rotate this so you can see it. On its side, can you see just this part here? That's like trigonal planar. Can you see that? If I turn it like that, can you see it? So we've got a completely vertical part, and then you have a trigonal planar center. There's not just one bond angle, there's actually 2. That trigonal planar center has a 120 bond angle, but if you look at it from the up down, that's 90. So this has 2 different bond angles. Okay. All right, let's keep going. Here's our next one.
Wait, was that polar or not?
Oh, I'm sorry. Trigonal bipyramidal, assuming all your terminal elements are the same, non-polar. Non-polar, symmetrical. That's why this is AP. These are the extended shapes. They're more complicated. What's my steric number here? 5. 4 bonded pairs, 1 lone pair. Now, here's the deal. It has a steric number of 5. So in your mind, guys, I want you to think, okay, it's starting out trigonal bipyramidal, but I'm going to pull one of these off and replace it with a lone pair. Does it matter which one I pull off? Yes, it does. Which is annoying, I know. But I'm going to give you an easy way to remember this, okay? And I'll turn this so we can see it. Okay, imagine this is your head, these are your legs, here are your feet. You have one arm out, another arm out, and you have a tail. Okay, I know that's ridiculous, but this analogy it's gonna work. So it's like you're standing like this, and you have a tail. Okay? We have to pull one of these things off. Somebody comes along and says, I'm chopping something off. You get to choose what you lose. Yeah, you're gonna lose the tail. Okay? If you're gonna choose your head, your legs, or one of your arms, you're gonna choose the tail. Okay, so I'm losing a tail. And I'll show you what that looks like. Okay? So that tail is now a lone pair. Yes, and I did not make this name up. This is for real. Seesaw. Now, why is it called seesaw? It's hard to see here, but watch. Okay, I lost my tail back here. Here are my arms, but if I turn it like this, seesaw, seesaw. My hands aren't big enough. Okay? It's like a seesaw. Okay? But it's also, you're missing a tail now. Yes?
Does adding the lone pair make the other bond angles?
You got it. Thank you for saying that. Yes. The bond angles, and this is, again, my only complaint with this simulation. Same bond angles as the row above in your notes, just less than. Less than 90, slightly less than 120. It's like everything just kind of got pushed. Like that. Okay. And what do you guys think? Does this look symmetrical to you from all angles? No, this is definitely a polar molecule. Okay? I drew this one for you at the beginning of class today. Steric number, please. 5. 3 bonded pairs, 2 lone. Let's come back to our gruesome example here. Okay? Here you are. You've already lost your tail. You gotta lose something else. I'm gonna go with an arm. I'm gonna go with, since I'm right-handed, I'm gonna lose my left arm. Oh, that hurt. That was rough. Okay? It's called T-shaped because it's shaped like a T. Okay? So at this point, you've lost your tail, you've lost an arm, you still have your head, your legs, and one of your arms. So it's T-shaped, but that's not quite accurate. It's like a sad T. It's like a droopy T. So there's actually only one angle here. What are you going to say? Less than 90. This is not symmetrical, so polar. And our last example in this family, so we did today, last appendage. You've lost a tail, you've lost your left arm. Both your legs. You want to choose both your legs or one arm? I'm going other arm. Yeah, you need to walk.
Oh, no, you couldn't go in a wheelchair because you don't even know what to do.
Folks, we're back to linear. We are back to perfectly linear. Did you leave something in there? Okay. Perfectly linear. What's the bond angle for perfectly linear? 180. Polar or non-polar? Non-polar. Ladies and gentlemen, you learned a rule in Chem 1 that worked in Chem 1 that doesn't work anymore in here. When you did shapes in Chem 1, you had a rule that said if there are lone pairs on the central atom, it must be polar. That worked for the simple shapes, not for the more complex ones. This is non-polar, ladies and gentlemen. We have a few more, but we're going to go quicker. You don't memorize it. You see it in your brain.
Yeah, Daddy.
What's my steric number here? 6. 6 shared pairs, 0 lone. Ladies and gentlemen, that is octahedral. Do you remember why it has the prefix oct? We talked about this. 8 faces to make it an octahedron. 90, 90, 90, 90. 90 all around. Okay. It is non-polar. Thank you. Yep, totally symmetrical. Okay. Now at this point, I'm kind of running out of examples, and every shape under the steric number of 6, you're actually not responsible for knowing, because scientists have realized that they can't find examples of some of these shapes, so you're not responsible for knowing them. But let me just show you what you are responsible for knowing. Okay? If you go one more where you have a steric number of 6, 5 shared pairs, 1 lone. Okay? And guys, if you look at this model that I've built here, this is a completely symmetrical molecule. Whoa. Do you think it matters which one I pull off? No. For this one, it doesn't. Okay? This is called square pyramidal. This is a shape you are responsible for knowing. Okay? Okay? So, remember, lone pairs take up more space than shared pairs, so this is not quite correct. What do you think? Angle. Just less than 90 is all you have to say. This next one, oh, sorry, polar or non-polar? This is polar. It's not symmetrical from all angles. Polar. The next shape is the last one you're responsible for knowing. If I have to pull off one more, which one do you think I should pull off here?
Top.
You got it. Top. Okay, so let me do that up here. Let's get rid of one of these shared pairs and add a lone pair. Ladies and gentlemen, this is the final shape you're responsible for. It's called square planar. What does planar mean? Flat. It's a flat molecule. It's a perfect flat X. Look at that. Perfect. And that is accurate. It's exactly 90. I'm sorry? No, I can give you some examples.
Wait, yeah, stop.
Here's an example for square pyramidal. Here's an example for square planar. Beyond that, they can't find any out in nature. Okay? So you're not responsible for knowing them. But would it be that difficult? You guys could actually figure this out. Watch. If I remove one more and add a lone pair, T-shaped. Yeah, it is. If you were going to remove one more, what would it be? Linear. But they can't find out in nature a molecule that exists with 4 lone pairs and 2 shared pairs. So they say, don't worry about it.
I mean,
Oh, square
that
planar?
was
Yeah, square planar is nonpolar. It says, ladies and gentlemen, listen, it says do not memorize.
Learn.
Learn. That doesn't mean, oh, you can use this chart on the test. It doesn't mean, oh yeah, sure, you can use the model kits. Mm-mm. When I say don't memorize, that's that's like my hope for you, is that you won't have to memorize. But for those of you that truly, and I understand that there are people out there like this who truly cannot visualize this stuff in your brain. I get it. You may have to memorize. You may not have any other choice. What I'm hoping, though, is that at least your memorization could be a little easier in the fact that we went through these shapes in groups. Like, we went through what is the steric number of 5 and anything that comes from something with a steric number of 5. Okay? We started with a steric number of 6 and went down from there. Okay? But guys, on this next test, I've seen people do crazy things. And you do what works for you. I've seen people go into almost like a meditative state. And like they close their eyes. And I see people doing like, I mean, hey, whatever you gotta do. You know, at the end of the day, it's whatever you gotta do. Now I have a gift for you. Yep, a gift. And when I give you this gift, you're going to be mad at me that I didn't give it to you at the beginning of class.
Oh.
It's a chart with everything that you just wrote down. What? Why'd you make us write it all down? The act of actually writing things down improves memory.
You said nothing.
Walked into that one. It's fine. Improves learning.